Welcome to your presentation for Structures 2. Our group is 33. This presentation will cover the design of a steel structure, and the following members were designed: purlins, wind brace and strutting, rafters, and the central column. The first step in purlin design is to find the purlin load width. This is important for finding all the dead loads. First of all, the internal and external spans were found. This is done using the following equation. The dead loads required for purlin design are roof cladding, purlin self-weight, ceiling weight, insulation weight, and service weight. For the dead loads that were on an incline, such as insulation, the span between the purlins and roof angle were used to find them. There is a list of the dead loads below. To calculate live load, Australian standard 170.1 will be used. This standard states the minimum live load must not be below 0.25 kilopascals. Our live load is 0.514 kilopascals, so it is above this threshold.
Wind loads. The location of the shed structure is in Adelaide, thus making the wind region for said structure to be in Region A. This is known as the wind region categories are given in the Australian standard for wind loads for housing. The wind terrain category for the said structure falls into Terrain Category 3, TC3. As such, the shielding for the shed structure is partial shielding. The topographic class determines the effect of wind on a house because of its location on a hill, ridge, or escarpment and the maximum height and slope. The given topographic class for the shed structure is T3 in accordance with Table 2.3 in AS 4055-2012. The wind class is given in Table 2.2. This classification is a combination of wind region, terrain category, topographic class, and level of shielding. As such, the wind class for the shed falls under N3. Once the wind class has been established, Table 2.1 is now looked at to establish the design gust wind speed for non-cyclone regions A and B. From this, we can see the ultimate limit state, serviceability limit state, design wind pressure, ultimate limit state, normal to surface, design wind pressure, normal to surface, and the wind pressure times load width. Now that the wind, dead, and live loads have been calculated, they will need to be entered into the load combinations for the strength limit state equations using the values found within Table 4.1. After inserting the known values into these equations, we will get the ultimate limit state, which is 2.55 kN per meter inwards force and 2 kN per meter outwards force. According to the standards, these will be the maximum forces exerted on the purlins.
After the ultimate limit state has been found, the section can be assessed against the strength limit state. A double lap purlin will be used with the lapping over the central rafter. With the maximum unbridged span, a general rule of thumb is 20 times the section depth, which works out to be 4 meters in this case. Using the LISAC brochures, we can determine the maximum kilonewton per meter of section. Doing this is determined that Z219 is a safe purlin. Australian standard 170.1 states the equation and wind factor for serviceability below. This standard also states the equation for maximum deflection allowed within the structure. Using this, we can find the required load for max deflection and compare it to the one in the LISAC brochure. Doing this, we can conclude that this section is safe for use on both strength and serviceability limit states. The purlin brochure states the required lap length for spans greater than 6 meters is 900 millimeters. We can use the following equation to find the length required of the purlins. Doing this, we find that the section needs to be 6,520 millimeters long. For the wind bracing, the client has specified that equal angle section will be used, and we found that one bay of the 2-bay structure is a more economical choice when bracing a structure. To design the bracing, values found in the wind bracing section will be used again. The first step in designing wind bracing is to find the area of the profile of the shed. To do this, the structure is broken up into two parts, a triangle for the top of the roof and a rectangle for the main part of the structure. When this is found, it is divided by 2, which equals to 17.45 meters squared. As the profile of the structure only has 2 columns, each column will carry half of the pressure and half of the suction. The pressure and suction calculated by the wind loads times the area will give us the pressure that each column will carry. As shown on the right hand side, the bracing we went with is just a simple cross bracing spanning over the entire roof span. From this we can deduce that the diagonal members will have 0 forces in them, but we still need to find out the reaction from the structure, which is a combination of all the loads divided by 2, which is the pressure and suction added together, which is 23.1 kilonewtons. Doing this we can find the strutting member, which is down below, and the section is 168.3 by 4.8 circular hollow section. The structure had 2 different types of walls, so 2 different separate forms of bracing, one side being 4.5 and one being 4.22 meters. The compression members in the wall bracing are first assumed to be 0 force, and the moment around section B was found, which turned out to be negative 16.25 kilonewtons. After this, theta and F1 were found using the method of joints. Doing this, we can determine the forces going through the diagonal members is 28.26 kilonewtons, which allows 50 by 50 by 3 equal angle to be used. In conclusion, the roof diagonal bracing had no forces in them, which allowed the smallest use of section, which is a 50 by 50 by 3 equal angle. Subsequently, the forces in the wall bracing was small enough to allow the seam section, and the strutting is 168.3 by 4.8 circular hollow section.
Rafter design. Dead load calculations include all aspects of the roof, such as roof sheeting, self-weight of purlin, ceiling, insulation, surface weight, and owned weight of rafter. Calculations of these dead loads are similar to what has been previously calculated, with the only difference being the weight is multiplied by the load width being 6 meters. As we can see, the dead load calculations have been previously calculated and are multiplied by the load width. We have assumed the self-weight of the rafter to be 100 kilograms per meter. Live loads have been calculated in the early stages as per table 3.2 for roofs. As it was for live loads, wind loads have been previously calculated, and thus those results will be taken and worked on. Now that all the loads have been calculated, we combine these loads as per the combination action of AS1170 section 422. From our load combinations, we see that the highest sum shows the compression force on the beam, and the resulted reversal wind action being generated being the lowest sum. The top flange of the I-beam is under compression. However, the purlins provide the lateral restraints for rafters. Therefore, the top flange of rafter is restrained laterally against buckling, and maximum unrestrained length of the rafter is 1.78 meters. As we have the maximum unrestrained length and the moment factor, we can use the capacity tables to design the members. With the graph, you use the maximum unrestrained length on the bottom to mark a line vertically up, and the moment sum is used on the left side to mark a line horizontally. Now we check the beam for reversal actions. This time the beam flange is under compression and there are no lateral restraints for the bottom flange, and the effective length is 8 meters. These calculations were also done using the end rafter section, and the maximum deflection was found to be 16.41 millimeters, which also falls well below the serviceability requirements. We have chosen the section for the central rafter. This rafter well exceeds a stronger design load and performs better than the allowable deflection. For the end rafters, all the loadings were halved to find the values, as the load width for the rafters were 3 meters.
Column design. Designing a typical column supporting the central rafter. The bottom photo is a representation of a typical column supporting a central rafter. The top photo is a bird's eye view drawing of the structure with the column circled to show where it is positioned. The diagonal line represents the supporting areas of the column circled. Dead loads. The dead loads below are from ceiling 1.5, insulation 0.035, surfaces 0.48, roof cladding 0.29, purlin weight 0.07, rafter self-weight 0.2. This gave a grand total of 2.575 kPa for the total dead load. live load. To calculate the live load, the following equation from the Australian and New Zealand standards 1170.1 will be used. The answer is 0.195 kPa, so we should consider 0.25 kPa for the live load. Therefore, the total live load equals 6 kilonewtons. Below are the equations and results for the wind loads. The wind load from wall will not generate any axial force to the column. Load combinations for N and M. Below are all the equations and results for N and M. Case 1 and 2. Case 1, N maximum equals 83.16 kilonewtons and Mx corresponding equals 0. Case 2, Mx maximum equals 14.27 kilonewtons per meter and N corresponding equals 74.16 kilonewtons. Universal columns is to be the chosen suitable cross-section by using the capacity tables. Column design. Using all the graphs and tables, the results for case 2 resulted in safe, with the following equations and results showing it to be safe.